happy hour. I'm Eric Smalling. I'm a developer advocate at Snyk. It's only 12:30 where I am in central US, so I don't get to drink anything as interesting as probably half of you are doing right now. But we'll get started in just a second here. Give people a few seconds to roll in. A little about myself while we're waiting. I'm a developer background. I've been developing for about, I don't know, 25, 30 years, but the last decade or so, been Kubernetes and Docker centric, doing a lot of, well, not a full decade, I guess, because Docker's only 7 or 8 years old, but I was using it back in the .7 days, but been consulting around it and cloud native technologies for that time. I'm just going to go ahead and kick in, and this is pretty informal, being a happy hour, so as people roll in, we can catch them up if we need to. What we're going to talk about, I just talked about myself, so I'm a senior developer advocate at Snyk, and that means I help developers learn how to do security, how to apply security patterns to their workflow, supporting what we like to call the DevSecOps methodologies. Today, what we're going to talk about is some of the attack vectors we see out there today in cloud native. And we're going to go through a few issues we see around security context, excuse me, and resource limitations, which are some of the most common misconfiguration areas that we see happening. And I'm going to show you a little bit about what can happen if you don't pay attention to those things. Then we'll wrap it up, of course, at the end. We're going to start out first by looking at why distributed cloud-based systems are complex from a security perspective. Now, one of the most well-known security breaches that's happened over the last few years targeted Capital One Bank. It affected about 100 million users in the United States, ended up having, I've heard anywhere from $100 to $150 million impact on their bottom line in fines and lost revenue ops. It's a good example how misconfiguration in a cloud system can be catastrophic from a security perspective. There were a lot of factors involved in this, from permissions and RBAC through misconfigurations in web application firewalls, exploitable vulnerabilities. And the real takeaway, though, was that distributed applications we're building now are really significantly increasing in complexity, with lots of different systems which may or may not be under our control, and they're all interacting together. Taken as a whole, this means that it's easy to misunderstand how it's all glued together. And that makes it easy for something like this to happen. Now, if we take a look at the story of the last decade or so in software development, it's really been around where we've seen the boundaries of what is an application, what is operations, and what constitutes infrastructure, those lines being increasingly blurred. The old view of the world was that the application was the only piece under the responsibility of the development team. All the other elements of the stack sat under IT operations or other teams, and security was usually a step right at the end of the deployment process that happened at the end of your pipeline. The world we live in today is one where infrastructure workloads are completely tied together. GitOps is a really good expression of how intertwined things are today. Everything gets declared as code, everything is software development practice. There's no real difference between our workload and the computing infrastructure that goes along with it. By infrastructure, I don't just mean the underlying compute technology, but also the configuration and the operational policies that control those capabilities. As a community of practitioners, we've discovered, excuse me, I can't talk today. Trust me, I'm not drinking anything like LaCroix here. As a community of practitioners, we've discussed in immense detail this blurring and eventual consuming of the boundary between development and operations. But in a lot of cases, we really haven't considered how that impacts how we model and practice security. In many organizations, security is still considered to be an external practice, somehow existing only when our applications are deployed and operational. But this is unworkable in the era of continuous integration and delivery. As we've seen, development-driven teams now have responsibilities for most of our deployment stack. So this gives those teams a much greater responsibility for ensuring that those things are secure. By the time our code and our infrastructure is deployed to production, it's too late to deal with implications of security issues. We can't slow down the velocity to introduce security gates in the way that things used to work. Velocity and time to market is one of the clear differentiators we have now, and we need that to be able to succeed. So that presents to us a set of unique challenges around security. How do we make sure our applications and infrastructure are secure when our working practices are evolving into those super fast delivery pipelines? Security still matters, and as we've seen repeatedly over the last few years, security breaches can have a massive impact on business, both from a financial perspective in terms of bottom line, potential fines, but also on how trusted our customers are of us. And trust is really one of those key metrics in the cloud era. When we start to look at all the different elements that we might now be creating as part of our application stack, we have our source code, we have our third-party dependencies that might be being brought in like as modules, Docker files, IAC, stuff like Terraform, and then what we're going to be talking about today, which is our Kubernetes manifests, which is obviously the configuration of your app under Kubernetes. This is a lot to take in, and for developers, I have to understand in depth all of this stuff and be able to make assessments on how secure it is. I mean, it's a lot just to get the stuff working. So luckily, Kubernetes itself does have some levers built in that we can use to control some of the aspects of securing our clusters. The first one we're going to talk about is security context. Security context, it's a set of configuration flags that are defined in our YAML files, which control certain aspects of cluster security. Sorry about that. Very simple definition of what these flags is that they define the privilege and access control settings for a pod or a container. Here, you're looking at a simple YAML file definition for a pod, and we can see that we have a security context section defined, which in this case sets the privilege flag for this given pod, and that allows it to operate in a privileged mode. Then it sets some capabilities for the pod, which are privileges that are controlled by the Linux kernel. We'll get into these in a minute, what they actually do. But there are a lot of other flags that you can set in this section as well. We only have time to talk about a few of them, but these are the first ones we're going to hit on. So the first place we're going to start here is with these privileged pods. Privileged means that the container has basically all the things. They can, processes running in the container, in these privileged containers can pretty much do anything, from access to the hardware, to host file system access. It's basically root. That's clearly dangerous from a security perspective. If this pod gets compromised, then an attacker can basically do whatever they want. Now, there may be good reasons for running something in privilege. Perhaps you need direct access to things like GPUs, or you need to manipulate the network subsystems. But in most cases, most processes don't need this and really shouldn't be running like this. Kubernetes does have granular enough permissions in most cases to be able to give containers what they need. And in most cases, running privilege is just the path of least resistance when folks are first deploying something. And it's just the easiest way to get things to make them work. So let's take a look at a demonstration of this in action. And what I'm going to do here is deploy two apps into my Kubernetes cluster. One of them is a mock-up of a payment app. It's not privileged. In theory, it's isolated, and it writes to disk in a JSON format, which will represent as our secure data. The other app is running as privileged and has a remote execution vulnerability that we can exploit. Now, because these apps are running on the same node, therefore using the same container runtime, their image layers are stored in the same file system. And we're going to see how an attacker with access to the vulnerable pod can access the files of our supposedly secure payment app. Let me get out of slides here. We'll jump over to my terminal. Now, I've already deployed something to my cluster. If I do, K is my alias to kubectl. I'm just too lazy to type. So if I do a get all, we can kind of see what's running. We have a pair of deployments, which have their replica sets. And here's the pods that they're deploying. There's that web deployment and a payment deployment. Let's take a look at what those are made of. So we kind of have a level set here. Let's look at the payments first. And the application itself, sorry, let me make sure I'm in the right directory. The application itself, the image that is running for the container is running off of, simple PHP app, nothing complicated. You can see it comes from PHP 7.4, and at runtime it's just running PHP, nothing complicated there. The Kubernetes deployment, if you've not seen one of these before, this is just simple single container, single replica deployment. It has a label app payment. It's running on an image that I've built locally. This is all running locally so that I don't have to worry about external dependencies for the demo. But you can see down here in the configuration, we do have, let me scroll down. We have the container port, we have a liveness probe, but we don't have any security context set for the payment at all. So it's taking defaults. And by default, privilege is false. We jump over to the web tier of the app. The Docker file for this, also nothing complicated. But if we look at its deployment, it has same kind of information, all pretty much identical to the other one, except that its security context is set with privilege to true. Now, if say I'm a developer or DevOps engineer coming in and looking at this for the first time, I'd be scratching my head right now. Why does this need to be privileged? And I'd be going to talk to developers to find out why. But let's see what can happen to you if you have that set. So I'm going to first get my notes over here on the side. Set up a variable so that I can type things easier. So make sure that's set up. So there's my IP of my host, and that didn't change. So let me refresh this. Sorry, I was testing the demo beforehand. So this is the simple web tier part of this app. It's just you can upload images with a comment, and it's just a contrived little app we've made. And the coloring's off on this, but you can see support us at the top. I love this app so much. I'm going to donate to this app. So let's put in a fake credit card number. And that expires, who knows, in the future, 1, 2, 3. And we'll send that in. Thanks for your donation. You're welcome. So we'll come back out here now. I'm going to refresh this. Now I'm going to use the app a little bit. So let's say my name is Joe Hacker, not Hawker, Joe Hacker, or some combination of text. For a picture though, instead of uploading a picture, I am going to let me show this to you before I do it. I'm going to send this PHP file. So if I do a PHP, you can see that this PHP file basically echoes out a var dump of a system call. Horrible, but that's what it is. So let's go back to the app and choose that file. I'm going to upload that. And there we go. Now it's trying to represent this and it can't because it's a broken image link. I'm going to inspect that because what I want to see, there it is. There's the unique ID that got assigned to it by the web app. So I'm going to grab that and copy it. Okay, let's go back to my terminal. And now I am going to make another variable. We'll call it ingress. I'm sorry, we'll call it image, sorry. Equals HTTP. And we're going to paste the ingress I grabbed earlier and then that to it. Now, if I use the curl tool to get at that. Actually, before I do that, let me show you something. Get pod. So we have, those are the 2 pods running. If I exec into one of these pods to kind of see what's in there, I'm going to jump into the web pod, give it its interactive and a TTY. And we're just going to run bash. Oops, what did I do? Helps if I type the command right. Live demo. If I go into the temp directory and look, there's nothing in there right now. It's completely empty. So we'll pop back out of here. And now I'm going to run this curl, and I'm attaching a few arguments to them. I'm saying command equals make dir space temp host. Because our application has that vulnerability in it, now if I go back, I'm not going to shell in, I'm just going to do an ls. We're going to look at temp. It's created a host directory. That host directory is empty. Okay, bad. But let's see what else we can do. I'm going to take another command now, paste it in there, and you see here, what I'm doing now is that the URL encoded mount of dev VDA1 blah 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 to temp host. If I do the ls of that temp host directory now, that is the dev VDA file system from the machine, from the host itself. Because I'm privileged, I can do that. And now you can imagine what all I can do. So let's say I know through some social engineering I've done that I'm looking for a file that's called cards.json. So I'm going to do a find on that. That is in the other container that happens to be running on the same host. So let's see what's in one of those paths. I'm going to grab the last one here. And that one doesn't have the card I just gave. It's got some other cards though, which is bad enough. If I went through others, I could find the one I just put in there. But that is showing you that if you have a privileged container running in a pod, all bets are off. They can get in. They can start looking at other containers that are secure, supposedly, because you've given them full access. So the next thing, hold on a second, slides. So that's bad. The next thing I want to talk about, though, also related, kind of somewhat related to this, is root containers. So it's relatively easy for most people to not realize that a lot of container images are actually running as the root user. If we don't define a user in your Docker file, for instance, then that's what you're going to get by default. All processes inside that container are running as root, UID 0, as it relates to the context of the container. This is slightly different than running with the privilege flag, since the container runtime isn't going to give you all the additional capabilities that you get with privilege mode. And there are some other differences, like if you're using things like SE Linux, but you're still going to get a bunch of privileges that you may not want to give. Again, there are going to be use cases where you might actually need to run containers as root in their container. Perhaps you want to do things with the container system itself, add users or groups, or perhaps you need to install some packages or do something for some reason at runtime. There may be some network operations or something that you want to do, or work with external volumes. But doing this, running as root, is a security risk. There's plenty of stuff we can do if an attacker gets access to the container. We can access certain files, especially if things are mounted. We can exploit the network. We can potentially access other containers in a similar manner. Again, depending on what's mounted to it. So how do we manage the need for additional privileges against not running everything as root? How do we manage that need? Well, there's this Linux capabilities. That's where they become useful. Capabilities are a function of the Linux kernel, and they allow for more granular access to raised privileges. This was originally designed to allow processes to have raised privileges while they start up to configure network access or something. And then once configured, they drop down to a smaller set of privileges for the remainder of their operation. In the container world, we can use capabilities to manage the privileges that our containers have in a more granular way than just granting root. We should always be guided, though, by the principle of least privilege. Just give the container what it needs to operate and no more. We can start along that path by dropping all capabilities and then working out which ones we actually need and just granting those. So let's take a look at that in practice. Jump back over here. And so I'm not going to go through, hacking into the app right now. What I'm going to show you, though, is if I, actually, I kind of skipped forward in my demo. I'm sorry, I didn't show you how to fix the prior problem. Told you, happy hour, less formal, kind of jumping around. Let's first fix our privilege problem, and then I'll show you the capabilities. So if we go back into the web tier, I'm going to edit the deployment YAML. And now there's a couple of things I could do. I could delete the line and redeploy. I could comment it out, I can redeploy. But personally, I actually like explicitly having it in there with a false setting. Because in a real world situation, I'm going to check that in, go through code review, whatever, and it's going to be documented that I explicitly want this to false for a reason. So if the next time the developer that may have worked on it originally or some other developer has a problem, they're going to see, oh, that was, explicitly set to false, and we probably shouldn't be just willy-nilly turning that back on. So let's redeploy this, just so I can show you that what happens. And we'll get our pods, see what's going on. So we see the old one is terminating, and we've got a new web development pod starting up. I'm going to exec into that, and we'll just ls temp folder to show you it's a new container, new pod. There's nothing in temp right now. Let's jump back out to our application, and we'll see that it's a new container, so there's nothing in it. So we need to re-upload our hack to exploit it again. There we go. Let's inspect the elements. Come on, if I get my cursor on it. Copy. Check my notes over here. Okay. And reset my image variable. And now we'll just run that curl again. Get it back out of my notes to make that directory. Let's see if we can do that. Oops. Yep, there we go. That'll give me a little bit of heartache there. So it did. We were still able to make the host directory. That makes sense because we're still exploitable. It's not like we fixed that. But now let's try to mount that directory from the host. Let's look at, oops, go into the host. And now it's empty. In fact, if we look at the logs for that pod, standard out, you can see that that mount got permission denied. And that's because we simply said you can't run privileged. Now, we fixed that, but let's see what else we could do in that container. I'm going to exec in again. And you'll see right away that I am root, because this is a default container. It didn't have any user definition on it. And what could I do in here? Now, I could do these all through curl if I wanted to. It's just a pain in the butt to type those. So I'm just going to do these right here while I'm exec in. Imagine I am a hacker and I have gotten access to the application through a remote code execution exploit, and I started up a remote shell maybe using GoTTY or some tool like that. And I'm now going to do an apt-get update install. I can, because A, I'm root. B, apt-get's on the image, which is a whole nother discussion. But because I'm root, I can do that. I could do all sorts of things. Let's see, what can I do now that what I installed was some network tools. So I can, oops. I can see what my IP address is, and then maybe I want to run nmap and give it the IP address. And let's look at the /24. So nmap is a network scanning tool, scans the surrounding networks. Now I'm starting to see all sorts of interesting things like, oh, hey, there's a payment service that is available, and the DNS knows about. All sorts of, like, I have a beachhead now, and I can start doing things because I'm root in this container, and I was able to get some tools onto it. Now, even if apt-get wasn't available, curl is, maybe, wget might be there. So you want to make sure that tools like that aren't available to a hacker. But what if we were to limit the capabilities of this container so that they wouldn't have access to it? Let's do that. Let's go into the deployment manifest again, and right under this privilege section, I'm going to add capabilities, and then we're going to drop, and like we said, least privilege, right? So I'm going to say drop all. Now we would want to add, if this was a real application, we'd want to start adding the individual capabilities that we need to run the app. You'd be surprised how many apps though can run with all dropped, because they're just not doing anything that has a system call that needs them. So let's reapply that, get our pods, just make sure it came back up. The old one terminated, and we've got a new one. So I'm going to immediately just exec in, so we don't have to go through the whole exploit thing again. So I'm back in. I'm still root, but let's try to do our apt-get again and install those tools. Permission denied, operation not permitted. I don't have the system call capabilities, the privileges needed to install those things. So there you go. By simply just removing capabilities, you can protect against a large vector of attack right there. So there's another thing you can do. Security context also gives us another way of handling this root issue in addition to capabilities. So this this setting, run as non-root, it can it causes the kubelet, which is the piece of Kubernetes that starts, actually talks to the container runtime and starts the containers. If we set this to true, the kubelet will look at the image and the settings, and it won't let it run if it's root. So if you were to try to start it with this set, it would say, well, let's try this. So if I go back into, I'm going to get out of the pod, go back into this, and I'm going to add, put it in the middle here, run as non-root false. Oops, I'm sorry. Demo brain, sorry. That needs to be true. So what it's saying is make sure this runs as not root, right? So now we'll apply it again. Okay, get pods. Now we're getting a create container config error. So let's describe this new now the old one's still running because that's how Kubernetes works. It's not going to shut the old one down if the new one won't come up. Container has run as non-root and image will run as root. This is a great way to enforce with your developers. So as developers are writing images, you can tell them don't run as root, add a user to your image. But this actually, having this in the deployments makes that have to happen. They won't even be able to run without it. This is generally good practice. It's to enforce this. You could actually do full enforcement of this if you had a tool like OPA, Open Policy Agent, or pod security policies, although that's being deprecated. Both of those use an admission controller to actually stop configuration. So if, let's say you always want to run as non-root, you can configure those tools to stop any deployment that doesn't have that setting. It stops it right at the API level. So I'm going to, while we get back to the pod, I'm going to tear this down because we've got a different demo coming up here. I want those to be gone by the time I get back from my next slide. So let's change direction a little bit. Let's talk about resource limitation. This is a different kind of security issue. It's still important for us to be aware of, though, and to be implementing. So Kubernetes gives us control over the resources our containers need. The two most commonly specified resources are CPU and memory. It also provides two sets of controls for each, requests and limits. Requests instruct the scheduler to aid it in deciding which node to place a new pod on. Limits define the maximum resources that a container can use. So by default, pods run with unbounded limits, which means the only control in place is literally the available CPU and memory on the node on which the pod gets scheduled. The resources, if they're exceeded, then in the worst case scenario, we might start seeing applications getting killed as they run out. The important takeaway here is that you really need to be assigning resource limits to your applications. Kubernetes handles these two slightly different. So in terms of CPU usage, there's a throttling mechanism kind of built in. So when you get applications taking a lot of CPU, they're not going to get terminated. Our worst case here is they're going to get throttled and performance is going to suffer. So everything might start running more slowly. The more challenging resource to manage is usually memory. Clearly, memory is it's a finite resource, and when fully allocated, processes are going to, if they try to allocate more memory, they could be terminated or they're going to get out of memory errors when they try to get more. From a security perspective, This means that an attacker could potentially take advantage of that to perform denial of service attacks, either blocking users from using the app that's misconfigured, or worse, by doing it to other apps running on the same node, which would impact the other pods on that node. So let's take a example of this. So in this demo, we're going to deploy, again, 2 apps running on the same node. The first one we're going to designate as what I call our innocent app, and the second is our vulnerable app. The second app doesn't have any resource limitations set. So I've mocked up a potential vulnerability in this app that allows an attacker to generate resource usage. Let's go ahead and get this started up. Oops. Over to that directory and let's kick it up. So it's deploying the 2 apps. I didn't pre-cache this one before the demo, sorry. How are we doing on time? We're doing fine. Almost. Of course, it's going to be slow because I'm doing a demo. There we go. So now it is building the second image. You can see if you are looking at these logs, you can see these are Python-based apps. Good old pip install. Okay, so that is done. Let's check it to get my cursor to go in the right window. Okay, get all. Okay, good. So we have 2 pods, app 1 and app 2, with their services and deployments. Got a handy dandy little script here that should open them for me. Close this old tab to get it out of the way. You know what? Let's make this so we can put both on the same screen. I'll grow the font in a second. So you're looking at the 2 apps. So our innocent app is reporting here on its web interface that it has 6 GB total and 4 GB available to it. And our vulnerable app has 5, roughly the same, right? So it's running on the same node, so they're seeing the same amount of memory available to them. Let's now take this vulnerable app and back. Sorry, this. Oh, come on, demo gods, be with me. Copy the link. Easier to just type this. Oops. I say as I screw up my copy paste. Copy link, paste. So what we're going to do is we're going to allocate 100 meg and hold it for 10 seconds. In fact, I'm going to do more than that so it's more visible. Let's do a gigabyte and hold it for 10 seconds. If we refresh over here, you can see memory is dropping on this app, even though it's not the one being attacked. There it goes. So let's do 2 GB and hold it for 10 seconds. So you see it's going down, 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 and shouldn't die, but we get really close. Okay. So how can we protect against that? So what we should be doing, if we go into app 1, we'll look at its deployment. So you can see, oh, look, limits and requests were in here at one point, but somebody commented them out. So let's uncomment these and go find out from the developer why they did that. Reapply this deployment. And it has fired a new one up. So let's go back out to browser. Back to the top here. refresh this. This one didn't bounce, so it's still running. So if we look at this one, there's its values. And if I do the same allocation, allocate, and I'm just going to do something low first, just to make sure that works. That's fine. And if we refresh, we might see a little bit of movement over here, but not bad. But if we set our limit to 50, right? So if we set this to 100, it's not allowed. It's being told it can't. That shouldn't be a gateway error. Sorry about that. There we go. Failed to allocate. So the I don't know. My demo is freaking out. Sorry, but you saw the failure. That's what we wanted to see. It's not anymore able to take more than we told it can take. So it's not going to, in a well-architected system, be able to take memory away from the other apps. So that's all fun, good and fun. But how would I have known that before we started having out of memory errors everywhere? Well, this is one of the areas where one of our tools, our Snyk IAC scanner, comes into play. So I'm going to reset this back. Go back to where our limits aren't there anymore. Oh, fine. We'll just do it manually. Let me comment this back out. Now I'm going to run our tool. I happen to have it installed. It's just an npm install. It's free to get. And I'm going to do Snyk IAC test. I'm just going to feed it this deployment YAML, so it just looks at this one. This is going to go against a whole bunch of policies that we have out there for well-formed Kubernetes YAML in this case. And you can see it found a bunch of stuff. And one of the things it found was, there it is, containers running without a memory limit. It's also running without a CPU limit and a bunch of other things. So by simply adding that tool to a developer's tool chain, you could even put this in as like a GitHub hook or something, or a Git hook. You can catch this right on your desktop before you even commit your code. So about as shifted left as you can get. That being said, let's go back to the slides. And let me wrap up conclusions, and then if we've got some time left, maybe we get some Q&A if you've got any. So what are you going to take away from this, right? So the first thing is that for all intents and purposes, infrastructure and applications are now basically the same thing. We really can't separate our workloads from our containers, from our Kubernetes configuration. They're usually developed by the same team, often in the same repository. All of our configuration code needs to be considered as having the potential for security risks. Although because everything is now declarative, we have a lot of possibilities for static analysis on those files, like I just showed you. The responsibility for security needs to shift as far left as we can. We need to empower developers to make decisions about security based on modern tooling and processes, and to educate them about the critical issues in configurations. We also want to leverage automation here, both in our development pipelines and in our production systems, scanning our code, our containers, our configuration, all the way from our local development environments through our source code management tools, our CI systems, and into production. And although we've looked at a few of the issues you might want to think about around Kubernetes security in this, there's a lot more we didn't look at. There's RBAC, pod security policy, which again is being deprecated. I want to take a look at that. In fact, just today heard they opened a cap for the replacement for that. So look into that if you're using PPSPs. And just generally enforcement in general is a good thing to be considering for your clusters. Network policies are huge. If you're not doing that, please do take a look at the whatever CNI you're using, what it provides. And other settings in the security context, like SecComp, AppArmor, privilege escalation is another aspect of privilege that you want to look at. Tools like Snyk can help you here. We support scanning through Kubernetes YAML, as I showed you. It's part of our IAC tool. It also scans Terraform and Helm charts. We also have container image scanning, looking for vulnerabilities in your containers. Also in third-party libraries, open source scanning. That's kind of our bread and butter, what we started with. We also have, we just announced a free tier access to Snyk code, which is a static analysis for your code to see if you're doing security practices that are shady. And these are just slides showing us our tool. I already showed you the tool. So thanks for listening. I hope you enjoyed this. You can always come to our site, sign up, and get a free access to open source scanning, container scanning, IAC scanning. Basically, everything I talked about that whatever we have scanning for is free amongst what I talked about today. So you can do that. And there's my Twitter and LinkedIn accounts. Feel free to ping me there if you have any questions.